Okay, hello guys, this is Sanan, and in this video I'm going to show you the detailed description of how to model the tensile test. Um, and also apart from this, also I'll be including some of the instructions of how to model the composite materials, how to model the cohesive zone, and all these things, how to club them together. So we'll be going through these in a while. So just look to it, and just to remind you, I'm using Abaqus 6.14. So you might be using some other versions, and if you are using 6.11, if you are using a version below 6.11, then there might be possibility that the cohesive zone model that I'm going to use, surface cohesive zone interactions, might not be available in that. So in that case, a cohesive elements methodology can be used perhaps. So when it comes to it, I'll going to explain you more on that. For now, um, Abaqus CA consists of different modules, as you can see, and we will be generating our model through these different modules. So first is the part module, where we use to create the geometry of the product. So in my case, since I told you that this is the composite, what happened? Okay, so this is the composite. So and apart from this is composite sandwich between a metal, which is aluminum. So uh, we have aluminum, we have composites, and composite in oriented in 0 degree, composite oriented in 90 degree. Now you know that the specimen geometry that you used to make in this module is this may be yours own. So I have created this type of geometry. This is a typical dog bone tensile specimen. I have modeled only half of it because material or a geometric symmetry can be applied across this plane, across the plane of zx, across the zx plane. Um, a model symmetry can be applied. So only half of the model is generated, and typically I have generated three models: aluminum, whose thickness is around 0.6 mm, and composite 0 and 90 degree, whose thickness is around 0.5 mm. So this has been all done in the part module. Let's come to property module. So in the property module, what we have given is that we have given different properties to them. First of all, we have given aluminum. This is 2024 T3 aluminum. Uh, this aluminum has been given a homogeneous, solid homogeneous properties, and I'll just come to what the properties are. So considering it as an isotropic solid homogeneous, the properties are given to it. And similarly, for the case of composites, 0 degree, a composite layup is created. Since I am assembling all the layers, so in composite layup manager, only one of the plies are constructed, and after that I'll going to assemble all of these plies. You can have more than one ply also. There's no problem with it. So this has been pre-generated. So let's see what these terminology mean here. So this is the orientation. This is the global part default, the orientation in which the plies are stacked, and this is in element direction 3, that means in the z direction. So in this is generated by default region, whatever your region on which you consider that this is your ply, select that region. And this is relative element thickness, that means how much elements are there in along the thickness direction of the composite. So I have created 2 elements, so relatively that makes it 0.5, and this is the globally oriented coordinate system. Angle of rotation in this is 0, and the integration points are 3. 3 integration point means that the calculations are taking place on one layer, on the middle layer, and on the bottom layer, or top layer, bottom layer, middle layers. If I'll make it 1, then only in the middle only it will going to give the calculations. If I'll take 10, it will divide this layer in 10 parts. So accordingly, you know what I mean in that. So similarly, a 90-degree composite is made. Now it's important to realize that the material I have chosen in both of the cases is same. So when I choose the composite 90 degree or the composite transverse direction, I used to rotate it by 90 degree. So what it does, whatever the properties that you have, even of 0 degree becomes even of 90 degree. So a tensor transformation law is applicable, and that is why it is very useful to use composite layups. Otherwise, if this is not used, otherwise then you have to give the properties according to the 90-degree rotation, according to the 0 degree. So you have to manually actually transform the properties. But with the help of this composite layup module, you can, this can be done automatically. Okay, now let's come to the properties. What properties do we have? We have aluminum properties. We have, first of all, density. Density usually is not required in the analysis, but usually we used to include density to obtain the stable time increment, because this is the explicit analysis, and explicit analysis is an incremental analysis and requires a stable time increment. So stable time increment depends upon density and modulus of velocity. So only that, due to that, it is included. Otherwise, if you run this corresponding model to Abaqus standard, you don't require material density. Elasticity is required to follow the Hooke's law, and plasticity is required. So in plasticity, to show what kind of plastic hardening parameter you need to give, you can accordingly give them isotropic, kinematic hardening, Johnson-Cook, or any other one. So in this I have used Johnson-Cook model, where A, B, N is the this is the hardening exponent, M is the temperature exponent, melting transition temperature. And if you know what Johnson-Cook model is, you know what these parameters are. C is this strain rate sensitivity exponent, and this is the reference strain rate. So you know what these are, and I can club this with damage, Johnson-Cook damage analysis also. I have used perhaps, or instead I have used it in combination with ductile damage, as it is much easier to implement. So it requires 3 quantities: fracture strain, the strain at which your specimen has failed; stress triaxiality. Now this is a very funny term. Usually it is plotted in Johnson-Cook model. Actually, you requires this at different strain rate. So stress triaxiality is an important parameter. It gives you a 3-dimensional state of stress at the point of necking. So at the point of necking, before the failure strain, it actually gives you an idea of where the failure strain used to take place and where the stress gradients are maximum in 3 dimensions. That is what the stress triaxiality exactly represent, and it is the ratio of negative of pressure stress divided by the von Mises stress. So it used to, these 2 quantities used to get plotted each other, is fracture strain versus stress triaxiality. So a curve is obtained in this format: fracture strain on y-axis, stress triaxiality on x-axis, and kind of this kind of curve is obtained in that. So different materials have different behavior in that. Corresponding to which strain rate you are doing, put that. And this is a damage evolution. This shows when the damage used to take place, and this is determined with respect to the fracture energy at which the unit area of crack used to propagate. So this fracture energy is usually the area under the low displacement curve. So this is also used. So this is how the aluminum are defined. And similarly, for the case of composite, okay, again, for the same reason I require density, elasticity I required. In this I have used elastic constant. So you may use, if your material is kind of a lamina or transversely isotropic, you can use lamina also. If it is orthotropic, you can use orthotropic. The more exact you take, and it becomes more and more difficult for you because you need more parameters for it. Okay, so okay, this is what it is. Now a Hashim-Damage criteria is used because Hashim-Damage criteria is firstly it is inbuilt in Abaqus CAE, and apart from that it is the most widely used criteria in the literature. So it requires different strength, tensile strength, compressive strength, transverse tensile strength, that means strength in the 90-degree direction, transverse compressive strength, longitudinal shear strength, and transverse shear strength. So these data are required. And just to let you know, this is a typical composite glass, e-glass epoxy, where epoxy is LY556. So this data is available in literature, perhaps in the papers of P. Sodan, if I remember it correctly. This data is available, so you can go for it. And damage evaluation, again it requires energy, and it tells the program when to fail the particular mode. That means longitudinal tensile fracture energy. When the fiber is loaded in longitudinal direction, this is the amount of fracture energy, this is the area under the load displacement curve is. This is in compression, this is in again tensile but in the other direction, and this is in compression again in the other direction. So this all you need to obtain. Then there is some funny term called as a damage stabilization. I'll tell you why it is required. This is usually required to dam the system. Otherwise your fibers will going to fail very excessively, and this might in the explicit case this might terminate the program because of the excessive element distortion. So it's good to include a small viscosity coefficient or a small damping to a system so that elements doesn't deform excessively. When I add a stability parameter or the damping to the system, I am exactly increasing the energy of the system. So this is an artificial energy. So I need to make sure that these artificial energies should not be very large with respect to the internal energy of the system. So I try to check out that also. I have used the viscosity coefficient in the x direction or in the longitudinal tensile direction and in the transverse tensile direction. This is because I am only loading it in the tensile direction. So these two will not come in picture. So this is how the material module used to work. Once the property is done, I am going to assemble this. So this is what the assembly is. Okay, I have assembled it one by one. Okay. Okay, I'll do one thing. I'll call one more and try to show you how it is being assembled. I can call any one of them. Okay, I can call, for example, this 0 degree. Offset it. This is on. Then I choose this option, translate, check this, and I have to, for example, put it here. Used to put it here. So I put this or check this out and place this on this. So this is how the layers are assembled. Position is okay, just set it okay. So this is how all these layers are assembled. You can assemble in this fashion. So I just going to delete that extra one. Okay. So this is a very simple assembly module I have created. One by one you can assemble it together. Okay, now the step module. In the step module I am using an Abaqus explicit with some specific time duration. Since my composite and aluminum is strain rate insensitive, I can simulate it at a very faster rate. Okay, aluminum is strain rate insensitive strain rate insensitive below 3000 per second strain rate. Similarly, composites are strain rate insensitive below below 1000 per second. So when I take this in artificial time increment, this usually gives me the strain rate of around 50 per second. So that's very acceptable considering the composite and the aluminum we have, which have much higher strain rate sensitivity of around 1000. So this can be simulated very easily. Now I also use mass scaling to reduce the stable time increment that was there, that has been actually reduced due to the some bad elements. So I'm using this mass scaling also. Now what this mass scaling is and how it is done, I'm going to explain you when I'm going to check out the mesh module. Okay, so this is for now. I'll come to this afterwards because I have to explain you how these factors are also taking field output. Okay, come to the interaction model. This is important at this point. Okay, now just create three kinds of properties. Now it's very important at this that to create the cohesive zone, specifically the cohesive surfaces between two layers, you need to bring the surfaces under general contact for Abaqus explicit. Remember it. Abaqus explicit doesn't supports the surface to surface contact between the two layers when the cohesive model is activated. So in this case, cohesive model is activated, so bring the surface under the general contact. So if bring the bring the surfaces under general contact, just take it orbit self and come here, individual property assignment, because I have a metal layer and a composite layer, so the property assigned between them is different, and between the two composite layer the property assigned is different. Also you see there is a global property assignment, so this should not include the cohesive properties. If this includes the cohesive properties, then your simulation will not run. So you can give this any typical property like frictionless, just to make it sure that this doesn't work, because we don't have any other surfaces here to make the interaction. So this always self actually is misnomer here, and individual property assignment here. So we have 5 layers, 3 into 5, so we have 5 layers. So this is metal layer and composite layer. So this is metal to layer, this one metal to layer, then we have a composite to composite, this to this, this to this, and corresponding properties assigned. What is this property? We have created a property called as M to L. We have created a property called as L to L. Okay, that means layer to layer. Properties available within layer to layer, properties available in M to L, metal to layer. Okay, so this is being created. Now what are these properties? So we have M to L, L to L, and interaction property 2. We have 3 properties. Now let's see what these properties are. First of all, interaction property. I told you that this has created just to bypass that error ke Abaqus cannot use cohesive interaction with general contact. So just to bypass that error, I have used just a tangential behavior frictionless, just to bypass that. Then we have 2 typical L to L and M to L. L to L is a layer to layer property. Okay, again tangential behavior frictionless, or you can provide some penalty or friction if you want. This is normal behavior. There is no hard contact. Usually the default is hard contact, so I have taken it linear with a bigger contact stiffness. So the interaction between the two has a good amount of contact stiffness, and this is a default option that usually is there, hard contact. This is usually default contact, but there is no hard contact between the two. So I used to take it as a linear. Okay, then this is a cohesive behavior. Allow cohesive behavior during reported post failure contacts. Okay, only slave nodes initially in contact. Since I have bonded these 2 layers, so only slave nodes initially in contacts. Any slave nodes experiencing contact, that is not possible in this case. In your case it might be possible, like a tire rolling on a rolling on a road. So experiencing contact might be there when a rolls on a road. So that might be a case there. Okay, and traction separation behavior, you can provide the stiffnesses if you have, or you can use a default contact enforcement method. Come to damage. So what criteria you need to look, or what criteria you need to take, you must know in this. This is a quadratic traction criteria. So the maximum traction after which the failure took place. So this is the usually 85 MPa is the maximum amount of tensile strength the epoxy LY556 has when it has combined with, or clubbed with an hardener of M10 with 10% hardener. So this is what the shear strength is. This is the normal direction, this is in the other two directions. So usually this is there, and this might be somewhat lower, and this might be somewhat even lower, but for now, for the simplicity cases, I have taken it same. This will not going to affect that much. Okay, and this is damage evaluation again. Energy based damage evaluation we are taking. Softening, just for the simplicity I am taking it linear. If you are taking it exponential, you must know what you are doing. Okay, then there are three types of behavior: tabular, power law, or Benzic-Kane. This is usually mostly preferred because it gives the it makes the two modes, the mode 2 and mode 3, same. That is what the definition of Benzic-Kane criteria is. It makes the mode 2 and mode 3 same, and it gives quite a well results. So this is the fracture energy under the curve and the load displacement curve of epoxy, and usually the other fracture energy is usually double of what the normal fracture energy is. So you can count on that. And appropriate power law exponent can be taken. This is available in literature. Again, viscosity or stability or damping parameter is given here, so that during the contact there is no element failure, or there is no node to node penetration between the two, just to provide some stability of the system. Geometric properties, in this I'll provide a out of plane thickness to you. So whatever the cohesive zone thickness you wanted to put in, just put that. So cohesive zone thickness between the composite layers are small, and this is around 2e minus 5 between the two layers, and cohesive zone thickness between the metal and the composite layer is around, this is around 5e minus 5, that means around 0.05 mm. So this is a bit higher to that. So that is obvious, and the other properties are same in both of them. So in this way, a cohesive zone is defined in that. So once this is done, you can come to load module. Now this is geometrically what I need to tell you. Fix this part. Since this is a displacement boundary condition, fix this part. Make this symmetric and load this part. Okay, so it requires three boundary conditions. Fixing this part, since this is my x direction, fix this part. Or perhaps the x symmetry is not required. I'm sorry, x symmetry is not required again. That mistake. Okay, this part needs to be fixed. Okay, just a minute. Okay, so this was the fixed displacement that we were seeing, and caster boundary condition was used in this, and symmetric boundary condition about the y direction was used. Y symmetry across this, because I created a y symmetry here, and a displacement boundary condition, as I said, is used here, where a u1 direction, because it is an x direction, u1 direction, we apply a displacement of around 6 mm. Apart from this, Abaqus explicit also required you to give the steps or the amplitude in which this displacement is applied. So though in the Abaqus standard analysis you don't require to input the amplitude, but in the explicit analysis it requires the incremental step by step, and so you require to give this amplitude. Now how this amplitude is created, you just remember that what was your time step that you were given. The time step that you gave was around 0.01 mm. So you can use MATLAB for sure. In MATLAB you can generate it, like for example in this format. So in the MATLAB you can use from 0 to 0.01 small steps of point. This is 0.401 step size. You can generate the data in x and y direction with respect to time. So this will be the maximum amplitude, this will be the minimum amplitude. So you can generate the data. This is what your data is generated, about 1000 data points. So this will be your x data. I just transport this very well. This will be your x data. I'll copy this. Sorry, use this in Excel if I want. Sorry, made some mistake. Okay. Something happened wrong. Okay, just create a new file. This is the data that you have created, and similarly create the y data also. Something is happening here. Okay. No, something again happened there. See what there was some problem, I guess, with my mouse. It is double clicking, so no problem. This is what the x data is created, and similarly create the y data also. So this will give you till 0.01 mm. Okay, 0.01 mm time, and this will be your amplitude. So this is the time column till 0.01. What is your amplitude? So now in the y direction, your amplitude according to which your load is applied or your displacement is applied. So placed special, yes, it came now. So what you do, just multiply this a column by 100, so you will get 1 at the end. Okay, perhaps you will get 1 at the end. Okay, yes, you get 1 at the end. Copy this, because this will be your maximum amplitude applied at 0.01. What will be your maximum amplitude? Your maximum amplitude will be this 6 mm of displacement. I'm saying this as 6 because I've used it in meter, so I have to multiply it by -3. So multiply it by 10 to the power -3. So in that way this amplitude is generated. Okay, you know what I have done this. Okay, so this module is complete. Now similarly I'll use the mesh module. This is already made, but I'm going to create for you one. Okay, just first of all I'll delete the mesh. So I've seeded this as a part using 0.4 mm element size. So I've used 0.4 mm element size. So in 0.4 mm I have I've meshed all of these elements of any of the one layers, and similar meshing is applied on all the other layers. So any one layer I've used 0.4 mm, and then at this location, at the gauge, central gauge location, this is the location where my damage will going to take place. So I have to use much finer elements there. So I have applied, come on, edge. I have seeded it and used them in this format. Pick the edges and then applied around 0.2 mm element size. Okay. Then there is a control option, mesh controls, and just check it out and use the sweep technology, because sweep technology, what it does, it generates the element in a much better way around the curves, around these curvatures. So middle axis algorithm used to minimize the mesh, so it's better you take that and refine the sweep path. During the refinement of sweep path, remember that how your elements are generated will be important in this. Your elements will be generated along this thickness direction. So this direction you can take in this way or in this way, no problem. But in the other direction, this is also fine. But when it asks for thickness, always go with the Z direction. It's better that you should go in that. So first the elements will be generated here, and then the elements will be generated on the second part, because I have used two elements along the thickness direction. So first layer is of the elements are generated, and then the second layer of the elements are generated. So the thickness or the stacking direction is in this direction. So this is how the sweep is created. Okay, and then finally you have to give the element type of element. So in this we are using Abaqus explicit. So in composites we used to generate, or we used to have a continuum shell elements. You can use shell elements also, you can use solid elements also, but solid elements are not supported with 2D Hessian failure criteria. So for that you need to make a subroutine actually. Make a subroutine and then you can use a solid continuum elements. But since we have not made a subroutine, so in this by default I am taking as a continuum shell elements. There is something called as hourglassing also, which is not used as a default. Instead we will use a stiffness hourglassing factor. There is more written in the Abaqus manual is what is this stiffness hourglassing factor is. Just to know what this hourglassing is, in hourglassing mode, when the deformation took place, the elements which are bigger in size, bigger in size, there is only one integration point in between. Like for example, just consider that you have this element with you. I'll just show you by drawing the figure. Okay. Suppose that you have this element with you. So there is, just consider it as a 3D element. You have one integration point in between. This is called integration point. So suppose that you have one integration point in between. So since you have only one integration point in between, so when the deformation is made, when this element is deformed, this element is deformed at this point also, this element is deformed at this point also, this point also, this point also, and in these point also. But the calculations always took place at the integration point with respect to the shape functions of the element that we have. And shape functions are related with respect to the nodes. So with respect to the nodal displacement, or taking the account of the nodal displacement, shape functions are generated. And shape functions used to calculate the stresses or strains at the integration point. So your data is calculated only at the integration point. but this is not the exact data. If your elements is large enough, your there will be some deformations here, and these deformations are not captured by the integration point. So your element is deformed, but your integration point doesn't feel of that deformation on your and your stresses and strain doesn't feel of that. So there is a error in the calculation. So to account for that, we use hourglassing control. And for the case of composites, when you look into the literature, so there is some artificial stiffness that is used to incorporate inside the element, so that integration point actually feels that that deformation that took place at these points. So that is a hypothetical way of inserting a stiffness to an element. So in this format, or in usually we used to do stiffness in case of a composite. Okay, so that worked. Okay, then just remove this. I'll remove clear all. Okay, so in this way you can do that and just generate the mesh, part the mesh. So your mesh is created. If you have not, if you will not use the sweep technology, then your elements here in this region will going to deform and will not show proper meshing. So that is the reason I have chosen this. And always remember that, please check this geometric regions, like in the part module, just verify what the mesh is. Okay, so see if there is some so there is no analysis errors, no warnings, so that means your mesh is fine. Similarly, you can mesh the other two, aluminum, composite, other two also can be meshed similarly. Okay, fine. So this is all created. Then you don't need to go in the optimization module. This module is created just to optimize the geometry, so we don't need to optimize the geometry, we don't need to go in there. But we have left with something. Okay, I'll come to the step module again. Now, okay, just go there, and this is the field output request. What we need in the output is being given here. So first, output, whole of the model, what you require, stresses you require, strains you require, and all these things you require. Apart from that, you also require a failure, damage initiation criteria. This is for the whole model. Damage initiation criteria for the whole model. This will give you the damage at which the point at which the aluminum will going to fail. So damage initiation criteria at the point where the aluminum will going to fail. Okay, then this will going to show you. Also, this damage criteria, quadratic section damage initiation criteria, give you the point at which, or the time at which, the cohesive zone is initiated, or the cohesive bond is broken. So that initiation is also being given by CS quad SCRT. Or if you have taken the other cohesive zone criteria, then you could choose among these. Okay, this should remain in the whole model, or the whole of that model. Okay. Similarly, I have created 4 these field output variables also. These were there, something happened there. Okay, so these were created because I have 4 composite layers, and I need to see when the damage is initiated in these 4 layers. So 4 output criteria separately is created. In the first output criteria, first layer is put. In the second layer, third layer, fourth layer. Now what the output is required in this? First of all, the damages are required, and then the damage initiation criteria is required. Now you can question here that since you have used the damage initiation criteria, Hashing failure criteria, why you are not choosing these Hessian failure criteria and tension, compression, when I used to choose these, Abaqus gives the error that this Hessian failure criteria is not supported and blah blah blah. So that is, I think the internal error. What it is, I can't comment on it. But alternatively, you can choose a damage initiation criteria. Since this layer initiates when the Hessian failure criteria is fulfilled, so it will give you all the Hessian failure criteria by choosing a damage initiation criteria, the Hessian failure criteria that we used earlier. Okay, and I need it in the top layer, middle layer, and bottom layer. Remember that when we were creating the when we were creating the composite layer, we choose 3 integration points at the top, at the middle, and at the bottom. So I need the results at the top, middle, and bottom. So I have chosen this, and there is no need to choose any other criteria. That's fine. So Hessian failure criteria, all 4 criteria is only singly by calling this criteria, you will be getting the failure in all the modes: tension, compression, matrix tension, matrix compression in the first layer. Similarly, in the other 3 layers, this will happen. Okay, this is fine. In the history output, there is a need to choose the reactions. Now, how do I get the reactions? I get the reactions at the fixed point. This I have fixed, so I call the reactions here. I have created a set, X symmetry, and in this set I have called the reactions. So my reactions will be called at this. Then I have chosen a displacement. Oh, okay. So one node I have chosen. You can choose node anywhere, here, wherever you want to obtain the displacement. You can choose that node, save it. Okay, I'll tell you how to choose the node also. In the tools, there are different sets available. Displacement node, I've chosen the node here. Okay, and X symmetry, I've chosen the symmetry here. You know that. So just choose it. It will create a set and include this set in this. Okay, so just obtain the displacement only in the u1 direction, because we are checking the u1, so you can obtain the displacement here. Now the third is with respect to the energies. This is very important. When you are doing the explicit analysis, these energies will be very important to check that your model is right. Now all CD is the all energy that were there due to viscous regularization. That means the damping. When we were checking the damping we use the damping parameters in the case of composites. When we were modeling it in the material model, we choose 0.00007 and 0.01, I guess. So due to inclusion of that damping, what is the change in energy? So all CD will give you that, and that effect is very important. So see that these things should be very small with respect to the internal energy of the system. All I is the all internal energy system, all K is the all kinetic energy of the system, all SE is the all strain energy of the system, and all MW is the energy generated due to mass scaling. Mass scaling I have used, so this is the energy generated due to mass scaling. The energy generated due to mass scaling should be again small with respect to the internal energy of the system. Now how much small? People used to take it less than 5%, some people take it less than 1%, that all depends. But these energies should be checked. This should be very, very less with respect to the internal energy system. Similarly, since I am using a static, this is a static analysis, and I am using it as an explicit analysis. So kinetic energy should also be checked. My kinetic energy should be less than 5%, less than 1% of the internal energy. These all things should be checked. Okay, so once these all things are there, you can run your model, and then more results can be obtained. That just to check it, I need to figure out that these damage initiation criteria that I have chosen, Hessian failure criteria and fiber compression, matrix compression, all these 4 criteria are called through this single variable, damage initiation criteria. What these criteria are actually? Damage initiation criteria, okay, I'll tell you by drawing a simple figure. In the property module, okay, we have chosen, let's talk about aluminum and you will be more clear with that. Now, every one of us know that this is a typical stress strain curve of aluminum. Okay, this is the elastic part and this is the plastic part. This part is followed due to the Hooke's law. Sigma equals to E epsilon. Sigma equals to E epsilon. Okay, so my elastic part will take care of this part. After that, my plastic part will be there, which is represented by the Johnson-Crook model. Okay, and after this is reached, there is something called as damage, ductile damage. That means damage initiation criteria. This shows me what is my failure strain or the fracture strain. So this is the strain, failure strain will be around here. So this shows that how I have to go there. And the area under this will came under damage evaluation or the energy required. So this will be my energy, area under this. So if you have the experimental data, of load displacement curve, just check what is your sigma y naught, that means the yield stress, okay, multiplied with the fracture strain, okay, fracture strain, okay, divided by 2. So this will be your fracture energy G. Now if you see this is a typical area of the triangle. Okay, area of the triangle is half base into height. So this is my base EF and this is my height, maximum load, divided by 2. So that's the typical area of triangle. But this is not exactly representing the area of the triangle. So this is a kind of a tentative way of obtaining the fracture energy. Apart from this, Abaqus when uses the damage evaluation also uses how this damage is evaluated. So this criteria, damage evaluation, is used because the direction in which the damage occurred is not known in advance. So usually a parameter called as characteristic element length is included to know with respect to mesh when the damage is going to initiate and at which point or at which direction the damage is going to initiate. So the mesh involvement or the element size involvement is very important here. What is your element size? Multiplied this by this will going to increase the fracture energy definitely. So your fracture energy is increased and your result become more and more accurate. So in this case, you might say that ductile criteria will not exactly represent what this fracture energy is, because it is the area of the triangle and it is going something, about something around, not as the triangle will definitely will occur. This will be kind of a triangle, okay, this will be a triangle. So this will not kind of represent, you can say, but this LC will going to accommodate for this energy. So this is a tentative way of obtaining energy, because this is very difficult to obtain the fracture energy of the energy at which you obtain this fracture, because in the fracture mechanics you have seen that in the fracture mechanics the energy, how to obtain the energy is there, and that is obtained with respect to the crack length. So what is your crack length and what is your energy? You do a test, and in that test your data is obtained, and with respect to that GC is obtained. So one way of obtaining the fracture energy is that, but that fracture energy is very lower with respect to the amount of fracture energy there inside the load displacement curve. So I recommend you that if you have a load displacement curve, you can find the energy inside the curve. And the energy inside the curve can be obtained very easily. You can use a trapezoidal formula. Obtain one point here, obtain one point here. Okay, and what is trapezoid formula says? Area of trapezoid. This is the point. So area of the trapezoid can be obtained. You can see the formula for the area of trapezoid. It will give you the area between these 2 points. So in that way, step by step, create the area of the point of whole of this curve, sum all of them, and you will get the energy inside the load displacement curve. So in that way, the energy of, or the whole of the energy can be obtained for the case of composites. Similarly, for the case of okay, I have to clear all of them. So for the case of composite here, similarly, composites are much more suited to that formula that I have given, because the composite curve is actually, ironically, just look like a triangle. So your GC equals to sigma y naught multiplied by fracture strain and multiplied by characteristic length divided by 2 will be quite justified at this point, because the fibers and the composite as a whole, considered as a brittle material, feels like that. So in that way, you can obtain again, if you have the sigma y naught and your failure strain here. So if you have these two, you can obtain, and LC can be obtained. I'll just show you how the LC is obtained. Okay, how the LC is obtained. Go in the mesh, check, this will be the smaller elements, check them, size, edge longer than this, highlight it, this will give you the longest edge. So just take the average, maximum average edge, also take the shortest edge, and you can average both of them. So an average energy can be obtained. So this is one of the method I thought could be used to obtain the energy, because the energies are very difficult to obtain these energies directly, because you do different tests. So if you have the data for, in the case of composites, if you have the data for tension, compression, okay, for tension, compression, and matrix tension, matrix compression, if you have these data, then obtain the load displacement curve. You can obtain the load displacement curve through these formulas and add these energies here. So these energies will show you how this evaluation took place. These energies will tell you how this damage evaluation took place. Damage evaluation used to took place at D equal to 0, the damage is initiated. Damage is initiated. Okay, and in this format, D equals to 1, the fracture is, sorry, sorry, this is not D equals to 1, this is D, sorry, this is D equal to 1, not D equal to 0. So D equals to 1, this is your point where the damage is initiated, and D equals to 1, this is your point where your fracture used to take place. So this is a degradation variable, and this degradation variable is initiated when maximum stress or the Harshen damage is reached. So longitudinal tensile strength, when your longitudinal tensile strength in a tensile test is reached, your damage variable is initiated or is activated at D equal to 0, and then it progressively increased, D equals to 0.1, 0.2, 0.3, and till D equals to 1. The moment it reaches D equal to 1, it will going to fail. Similar happens with compression, tensile, and longitudinal matrix. All these things similar happen. So you have 4 damages criteria in this. You have DF, damage for the fiber. You have damage for the matrix. Similarly, you have in the tension and in the compression direction. So you have 4 damage variables: damage matrix in tension, damage matrix in compression, damage fiber in tension, damage fiber in compression. So 4 of these variables will go along this line and will go into fail your composite. So this is how this used to work. I will going to answer if you have any other questions in that respect. I want to answer all of them, and I request you to please subscribe this channel so that you can kind of make a group and we can have some discussion. You can perhaps increase my knowledge on that, and if I have made any mistake, you can make a note, underline the YouTube channel. So in that way I have modeled it. If you will encourage this, then perhaps I'll going to upload more of these manuals. Okay, thank you for watching this. This has been usually a very long presentation, but since I have explained more of these things, so it took it that much long. So thank you guys, thank you for watching.